Hello, how are you all today? So hopefully you should be all able to see me, and welcome to this second session on how we're going to create the breakout board and an update to have the Pong game all going live on the Basys3 board. So if we start working through this today, there's a few things before that I wanted to mention just before we work through that. So the first thing is, obviously, we will, again, be following on from the projects that we're using before. So if you can open up your Vivado project previously. The second thing is I'll just put this up on the screen, and you should hopefully be able to see this. If you did the first part or you want to work through the first part again, I've uploaded the first part to my video, to the Aduvio video channel. And what you can do is I'll put it in the chat, the message there, the link there, such that you can find the video there. And if you see other videos that you like as well, feel free to subscribe and watch those as well. So we're going to be starting today. We're going to be working through the second of the workshops here. So we've got the crowd supply workshop. So all the information is in the chat window. Megan's just pointed out the link to that second repository there. If by any chance you didn't get the first one to build along, or you had some issues, or you found the bug in Vivado that exists on Windows when you're generating high-level synthesis components, we could try the solution as well. So the Xilinx shell archive, which we're about to export from our Vivado design, is also available on the GitHub as well. So if you want to go to that one, you should be able to find the XSA there. Just in case you didn't build it or you wanted to start from scratch on that one, we can start from there. So let's take a start then. I'm going to move this across, and I'm going to share my screen. And so hopefully everybody can now see my my Vivado window. And this is the project that we created last time. And if you get any questions, please feel free to pop them in the chat or the questions bar as well there, and we'll try and answer them as we go through. So remembering back in last time in our Vivado project, we created this MicroBlaze system that had got the custom test pattern generator IP in there, and we got the so you can see these up here in our design. We got the test pattern generator here to generate the background. We got the custom heads-up displays, we were calling it, and that's going to draw the bat and the ball on the screen. And then we have the mixer element here that's going to mix those two videos together and create an output stream. The output stream, of course, would be generated by these elements. By these elements of logic down here, the video for AXI stream to output. Again, we were only using a smaller subsection of the outputs available due to the Basys3 board. But you can see here we've got all of the color channels, and we've got the vertical sync and the horizontal sync. And we've also got the 7-segment display, so the 7-segment display anode and cathode, and then we've got the push buttons, which we're going to use to control the positions of our bat as we're moving through this. So again, this is all based around the MicroBlaze. This is all based around the MicroBlaze. So we have the MicroBlaze in here. Just zoom across the MicroBlaze, and you can see we've got the MicroBlaze in here. Now, obviously, this is a softcore processor, and to get this to work, we actually need to write some software for it and download it and test it over the JTAG link. So we're going to do two things there. The first thing we're going to do is we're going to do a simple test pattern to work out whether a simple test program to work out whether the MicroBlaze is running correctly, and that make sure that we've instantiated the MicroBlaze correctly, make sure we've not got any clocks missing or resets held in the wrong way, etc. And then what we're going to do is we're going to take that and we're going to run through and we're going to take that and we're going to create another application which is a little bit more advanced. We can clone that from the from the GitHub repository. Once we've cloned that, we're then going to add that into the application that we've created, and that will give us the final application. And we're going to talk through exactly how we do that, and what elements are doing that in each of the segments in the code as we do that. And then finally, I'm going to show you how to actually generate the bit file and how to program that into the device, such that when you turn it on, the Basys 3 board should start playing this game, and you've got the bat and the ball, and you can see that there. So hopefully, to be able to move on with this project, what we need to have done is we need to have got this into a position where we've written the bit stream. So you should be able to see up the top here, it says write bit stream completed. Now this means that the tool's gone through the synthesis, the place and route stages, and it's created a bit file that can be programmed into the FPGA that will tell it all about the contents and instantiate the design. But to be able to program that MicroBlaze, we need a little bit more information than just what's in the bit file. So we need to export what's called the Xilinx shell archive from Vivado and take that into the Vivado software development environment, the Xilinx software development environment, which is Vitus. And it's within Vitus that we're going to write all these software and run through these applications. So what we're going to do, if we've got this write bit stream complete, or if you've cloned or if you're just following along from the repositories and you've just cloned the XSA from the solution under Lab 1, what we're going to do in Vivado is we're going to export that XSA now. So we're going to go to File, Export, and we're going to ask it to export our hardware. And on the dialog that pops up, we're going to click on Next. We're going to tell it to include the bit stream. So if we were working on a more advanced system, maybe where we've got a really complicated system, we've got lots of IP in there, and we're still trying to work through and get time enclosure and make it all work, and we've got a software team waiting on us delivering the hardware definition, we might include we might generate a pre-synthesis design, and that will just include all the memory map information and everything as it is, and all the IP information to allow the software team to begin to start working in advance with that. But as we're not at that position at the moment, we can quite happily pick it up and run from there. Sorry, a bit of a dry throat today. So we're going to include the bit stream in this, and then we're going to leave the names and the location exactly as we want it to be seen there. So we're not going to give it any fancy names, and we'll let it export to where the Basys Live was going to export. And what we'll do is we'll click on Next. In my case, because I tested this just before this afternoon, it's going to give me a warning that do I want to overwrite the existing file there. If you've not done it before, you'll not see this warning, but if you have, that's okay. Just click on Yes, and then on this final page here, we're just going to click on Finish, and that'll take a few seconds to export the hardware platform. So by doing that, we get to the end of the sort of step four in the lab book that you can get in GitHub. What we're going to do then is we're going to open Vitus, which I said is this software development environment. So we're going to go and we're going to click on the tools, and we're going to click on Launch Vitus IDE. So this is going to launch the development environment for Vitus. And now the first thing it'll ask you is where do you want to save all of your workspace? So your workspace includes all of the metadata files and the first stage bootloaders and the platform definitions and the application that we're going to create for this one project. Now, by default, I like to keep these wrapped up close to and you can literally store them anywhere if you want on your file system. By default, I like to keep these within the sort of the area that I have for my project. So what I'm going to do is I'm going to create at the top of my Basys 3 live project. Obviously, I've got in fact, we'll go under here. We've got the Xilinx project here for Vivado. You can see the sources, the simulation, the runs, the generated files. I'm going to create a new directory in here, and I'm going to call it Workspace. I'm just going to call it WKSP. I'm going to click on Create, and I'm going to click on Open, and it's there that Vitus is going to put all my files. So in a minute, when I import the XSA, it's going to be there where everything gets pulled through and gets started working from. So once Vitus launches, we can click on the maximize window if we've not already done that. And we'll see this range of options here that we have, from create application project to create platform project and create the library project. What we really want to do is we want to create a new application project. So we're going to click on create new application project. This first sort of tab tells you how the information is, how the project works, and how it all sets together with the processor, the domain, and the system project. We don't really need to do anything on that, so I'm just going to click on next on there. Once we get there, you're going to see all of the platforms that are installed by default for your installation. So you can see, because I'm running on a Linux machine and I use Vitis quite often to do acceleration, you can see that I have two Alveo cards and a Ultra 96 and a ZCU 104 installed on my design. But actually, I don't want to use any of those because I've not installed the Basys3 is not there. So what I want to do is I want to click on create hardware platform from XSA, and then I'm going to click on this one here that says browse, and I'm going to browse in my memory system. It always takes you to where the actual things are installed, but I'm actually going to go to my home directory. I'm going to go to where I saved my Basys3 project, so my Basys3 live, Basys3, and I'm going to find the XSA that we exported previously here. So I'm going to double click on this XSA. I'll leave that XSA there. I'm going to click OK on it. Now I've selected it, and you can see the timestamp. The timestamp is within the last few minutes. So we'll click on OK there to open that, and then we'll click on next. What we need to do then is we need to give the application a name. So we're going to give this an application name, say we'll call this Pong Live. You'll see automatically it's filling in the system name, and you'll also see it gives you a processor name down here as well, which is picking up on the processor that we're using in Vivado. So if you were to look back in Vivado, you'd see that the MicroBlaze there is named MicroBlaze 0, and that's the same one that we're picking up and we're running with in Vitis now. So we can click on next for that. And then we get a series of actions and domains that we want to do. So we're going to let it create a new domain because we don't have an existing domain. We're going to leave it running a standalone application, and we're going to, obviously, we've designed the MicroBlaze to be 32-bit, so we're going to leave it at 32 bits. Clicking on next will take us to a templates page. Once we're on that templates page, what we can do then is we can select any range of templates that we might want, template applications that we might want, to get our design up and running and to start us really to help us nice and easily with the design. So we could go for an empty application in C or C++. We could go for some lightweight IP, echo servers. If we've got some interest in doing memory or peripheral tests, then we could use these memory and peripheral tests. Or if we wanted to create a bootloader, then we could create a bootloader. For this one, just to prove that the processor's up and running and ready to go, what we're going to do is we're just going to create a simple hello world program. So if we leave that selected and we click on finish, then what we'll see is we'll see the project open for us in Vitis. And if you've never seen Vitis before, I'll just give you a little tour around Vitis. So this is our application, so this is our system application up here. We've got the application underneath it, and underneath that you can see the include files, you can see the source files, and up here where we've got the design one wrapper, that's the name of the platform. So we could perhaps named it something more sensible like Basys3 or something like that. But this is the name of the wrapper, and under the wrapper we have all of the standalone files. So the board support package has been generated under there. If we double click on the SPR, we get the option to change to modify, if we want to, the board support package. So the board support package really tells you all of the APIs and drivers that are used by the MicroBlaze processor to interact with its with the peripherals that are present. So we can set the standard in and standard out. We can change which drivers you use, particularly if we wanted to, for particular IPs. And we can see them down here as well. We can see the list of drivers that we have in this list. So you can see that we've got a GPIO in there. We've got the UART. We've got the HUD, and you can see all the way through. It's pulled through all of these drivers. So this is one of the real good benefits of Vitis. Actually, is that when we create a design in Vivado, not only does it pull through just all the memory maps and all the addresses and all the hardware specification, but it also pulls through all of the drivers that we might need to start working with those into this board support package, such that we can create our software application. Because really what we want to be focusing on is we want to be focusing on our value added activity, really, the little bit of fun bit of code that we're writing, and not just the not just having to struggle to write drivers to set register values in peripherals to get them driving. So we can do that. If we've got any libraries, we can click on the libraries tab, and you'll see any names in there. You'll see any libraries that we've got. We don't particularly have any at the moment. But if you had, for instance, the Zil Flash library in there, or the libmetal library, you'd see that. And if you want to see your address, the address space and an understanding of where things sit physically in the memory map of the MicroBlaze, we can click on the hardware specification tab, and you can see where all of these elements sit. So you can see where the GPIO sits. We can see where the UART sits in the address space and the size of the address space, and whether we're talking to a registered sort of interface or whether we're talking to a memory interface as well. So that's a really nice, powerful sort of ability to visualize and understand the system that we've got. If we close these now, what we can do is we can go to our source under the applications. We can click on the hello world.c, and we'll see a really simple hello world program. And I'm just going to change this just so you can. Just so as I can prove that I can't type, I can't spell, but just so that we can prove that it's working. So Carlos asked a really good question. Why do all the addresses start at the 4000 memory address? So let me just pull that back up again. And that tends to be, it's an element of where we're putting the local memory. So obviously in this case, our local memory is fairly small and fairly limited, but typically by default, Xilinx IP tend to drop in at the 400 million hex address. So it's a very common address range that you'll see across the MicroBlaze, across the Xilinx MPSoC. That seems to be that's the memory address region that's allocated for the AXI peripherals. So if you were to look at the memory map of the MicroBlaze, so where do we? Let's just click on the block again back here. So if you were to look at this memory, if you were to go delving into the MicroBlaze memory model, what you'd see is we've got the instruction and the data local memory bus, and we've got this here, the AXI peripheral memory bus. And if you were to follow that through, and we can talk about that offline if you want, if you've got any questions, but if you were to follow that through, you'd see that this address here, this 0x4, is the starting point for the AXI peripherals addressed to that bus. And it's not an unusual memory address. Like I say, you'll see it on the Xilinx. It's quite common across the Xilinx MPSoC. And off the top of my head, I've not tried it on Versal yet, so I don't know if Versal has that same sort of approach for low speed interfaces or not. So what we can do, we can come back to the application that we're creating, and we can see that we've got this hello world session here, and we're just doing two simple prints. Notice we're not doing printfs, we're doing print, and that's because we're using the Zil printf.h library, which gives us printf is actually a really big, it has a really big footprint memory wise when you use it and when you compile it. So this is a much smaller, much lower impact footprint that we have on that is there in the memory system. So we can do this. So we're going to change it now. So it just says hello world live session and successfully ran hello world. So not a huge amount. What we're going to do then is we're going to click on this hammer. Now we've set this to a debug release. So by default, everything gets to be included as a debug or a formal release. If you do it as a debug, it includes all of the necessary information that you might need for doing debugging, breakpointing, step pointing, single stepping, and such like. So what we're going to do is we're going to click on build. When we click on build, hopefully we're not going to find any errors. It didn't early on. We might find some warnings, but we're not too worried about that. It's going to run through. It's going to build you'll notice it's going to build this design one, the platform, and then it's going to build our application as well. And then it's finally going to give us this ELF file. So we've got this ELF file here. So what we want to do with this ELF file is we want to put it onto our board. But what we need to do first is we need to make sure our board's correctly set up. So if I include this, over my camera, obviously we need to connect it for the power and for the UART. With the board turned off, jumper 1, I think it is jumper 1. Put the jumper 1 in the position for the JTAG boot. So it goes across the two innermost pins, and then we can turn that on, and you should see, maybe you'll just see the power light up in the corner because there's nothing, because he's waiting to boot from JTAG, so there's nothing there. So what we're going to do is we're going to turn that on, connect it in, and leave it to boot from JTAG. Once we've done that, what we're going to do is we're going to click on this section down here, this debug icon here. We're going to right click on it, and then we're going to go to debug launch on hardware single application. So we're going to click on that. And what this should do is you should see it download to your design. You download the FPGA design to your design. So you'll notice magically my board's just come alive. So you'll see the 7-segment display has been set to all zeros. You'll see the done light up in the corner has been set to done there because it's programmed. And you'll notice that the application has been downloaded, and it's now sat waiting at the initial point to go. So it's now ready, sat waiting for us to control it and run it through. And we can, if we want to, we can hit this run arrow here, and that'll just run us all through the application, or we can single step it. But the first thing to do, because we want to see the hello world, because we want to see that as hello world, what we can do is we can open a serial terminal, and this is a serial terminal that I tested it on earlier on, so maybe I can clear the screen on that one, and we can work through. If I minimize that, maybe that'll work. If I put the two side by side slightly, so as I can single step through, and then we can see it working. So what we've got is, if I want to, I can control this by single stepping and stepping over the element. So we can see there's we single step and we step over again. That should have come up. Let me just connect again to that port. So the port settings are whichever port you're connected to, and then the baud rate is 9600. Let's try that this time. There we go. So I'm just going to relaunch this just so as you can see it running through again. Obviously, it didn't like my resetting the FPGA. If it comes to doing it a second time and running the application a second time, we can just hit on the debug. No, we can't because it's not picking it up there. So we can right click on here, we can debug, and we can click on the debugger icon that's already there. We don't need to click on the launch new one again. We can click on that. If it gives you an option about there being a debug session already running, click on OK. And we'll run around the loop again just one last time to make sure it's all good and running. Figures. There we go. So it'll run round again, and then this time round, we can see, there we go. I didn't put a line termination at the end of it, but we can see hello world from the live session. So now, hopefully, if you can see that, then you can see that it's at the same. We know that our process is up and running. And I can see in the chat there is a bit of a debate about why that address begins at 0x4. And that is the address that's set by the MicroBlaze architecture to look for peripherals on the AXI bus. And I think Rui made a good point that it's the ARM architectures do it. So I think it's very common for commonality purpose. I think the MicroBlaze is set up to behave in a similar way, even though it's not a Xilinx ARM. It's not an ARM core, it's a Xilinx developed core. But obviously, the more commonality there is in the environment, the better and easier it is for us to work with it. So now we've got that. What we know now is that our application is actually our MicroBlaze is actually working. And we can single step, and we can control it, and we can download applications, and we can run it. What we need to do now is create the actual application that we're going to use for this example. All we're going to do is going to switch back from. So if you'll notice up the top, we've got a couple of different perspectives. We're currently in the debug perspective here. So what we're going to do is we're going to flip over, and we're going to go back to the design perspective. Once we're in that design perspective, again, we can see all of our files and everything. But what we need to do now is we want to go and we want to find the right tab. We want to actually clone the repository. If you've not already done it, then we need to clone the GitHub repository, because that's got some of the code that we want, the software code that we want to use, in it. So I'm going to do this from a command line. If I can remember, I'm going to enter this commands git clone, and then I'm going to give it the location of my HTTPS of the GitHub repository that we would like to clone from. And it's the crowd. Can't actually type today. Crowd supply workshop 2. Who chose such a big name? I think that's right. And that should pull down all of the objects that we wanted. So if we were to open a file browser at that point in time, we can go under the Basys3 Live. We'll see now that we've got this new directory here, crowd supply 2 workshop. We could double click on that. We'll see what we've got. We'll see that we've got the lab books for this session. You've got the solution as well, the bin wrapper as well, the final programming file. And you'll see 2 files here, a new hello world.c and a thing called VGA modes .h. Any questions so far as we're moving through this? Feel free to ask any questions. So Marcus has asked a good question, and you can see it. You'll be able to see it work in the simulator, provided you give it a clock in the simulator. You'll be able to see it work, because I'm going to show you how to associate the bit files and how to generate the bit files and everything. Obviously, you won't actually be able to play the game, but you should be able to see it running in the Vitus, not the Vitus simulator, in the Vivado simulator. You should be able to see that running through in there. So now we've got these 2 files. What we're going to do is we're going to copy and paste them into the select them both. Copy. We're going to copy and paste them into our workspace, and under the application, actually. So we're going to replace the application. We're going to go into the Pong Live source, and you can see here where we've got the hello world.c application. We're just going to right click and we're going to do paste. And if we get a question about replacing these files, we're going to click on replace. And then back in nearly said Vivado, then back in our Vitis project, what you'll see is that we've updated this to include the application now, and that we're going to run. So you'll see that it's actually quite a simple-ish application. It's only a few hundred lines, long, and I'll take you through it. I'm not gonna walk you through every element of it, but I'll take you through it and explain to you what's going off, and then we'll show. So we'll spend a couple of minutes taking a look at this, and if you get any questions, please throw them in the chat window as well. So what we've got here is we've defined all of the include files for the different elements that we're using in our design. For example, so if you're not familiar with the xparameters.h file, so the xparameters.h file, it includes all of the description. It's the description of our system, of our computing system, the MicroBlaze system. So if we right-click on it, if we select it, right-click on it, and look at the open declaration, we'll see that in here it provides all the information about our design. So you can see that it tells it the clock frequency. So if we remember, we were running at 20 megs. You can see all of the information about the setup of the MicroBlaze, which is interesting, and that's obviously used to compile it. But where it gets really interesting is down the bottom is you can see what the additional parameters that we've added in there. So you can see, for example, the GPIO driver that we've added in there, and the name of the beginning address, the end address, the device ID. So this device ID is critical to use when we want to actually access that and work with that. So we need to know. So we need to include this xparameters.h to include that design, to include these device IDs and this entire description of the system when it's all compiled. You'll see we've got the GPIO. You'll see we've got the heads-up display there. We've got the UART light. We've got the video mixer, and all the video mixer settings. And we also should have down the bottom, we've got the video test pattern generator, so as we can see all the video test pattern generator. And then we've got the video timing controller as well. So we've got all of these elements that help us defined in our software, such that we can easily access them and work with them. And you'll notice each one's got a kind of a specific definition and then a canonical definition, and you'll find it's the canonical definition that's used in the software that we use. So it tends to be this definition that we're using, not this definition. So that xparameters.h defines obviously the entirety of the MicroBlaze subsystem that we spent the first hour creating. What we've got then is we've got a range of APIs that have been created by the board support package. So if you remember back here when we looked at what was included in the board support package, you'll see that it had got the driver, the GPIO, the HUD, the vMixer. What this created, and apologies because it's expanded it all, but for each of the elements, we've got a library element that's included to show the it's actually under here, the standalone DSP. We've got the lib sources is what I was looking for. So you'll see that we've got the lib sources for each one. Now you can't make any changes to these lib sources because the library is automatically compiled and generated, but you can see them and you can use them. You can use them for inspection to see what functions are provided, what parameters are needed. So we can go here, we can look at this. So we'll see that we've got multiple ones in there. So we've got the video timing controller, we've got the video test pattern controller, we've got the mixer, we've got the GPIO. You'll notice we've also got this xhudgen.h, and if we take a look at that, you'll see that this is as I mentioned to you, this HUD, this heads-up display was created in Vivado HLS. And one of the elements that you do in Vivado HLS when you create these designs is, as you package it and synthesize it and pull it through, Vivado HLS actually creates you all these drivers as well in software to allow you to ease your operation and ease your use with it. So you can see we've got this nice driver in in Vivado HLS that allows us to see, and you can see how we can do things, so we can set the ball, we can move the ball, we can set the bar position and move the bar position. So we've got all these functions that we can just call in our software application, and that will be translated into the registers of the appropriate IP that we're driving. So this one's generated, like I say, this one was generated by Vivado HLS. And if we take a look at some of the others, for example, the timing controller, we'll see all of the configurations and the settings for the timing controller. So you can see all the different modes that it's got defined, that it knows already, that it defined already. You'll notice the mode that we're not using is not in that list, which is why we have a different definition in there. But you can see it provides us all of the structures that we need to use. If you remember, the video timing controller is capable of either detecting the timing or generating the timing. So we need to be able to select between whether it's picking up the data from its registers or whether it's picking up the data from the input timing. So there's a lot of structures, a lot of data here that's present to allow us to do that. So we have these include files, and these really give us the the structures, the APIs to be able to easily drive our IP that we've added in there. What we've done next is we've defined a number of global instances for each one of them. So, for example, we have the video timing controller, the video test the test pattern, and the GPIO. We've defined an instance for each one of these, and then we've defined a configuration pointer for each one of these as well. And we've also defined a video mode. And because I was obviously being a little sloppy when I wrote this, we've also got some of the video mixers, the video mixer in the hood, and the video timing controller are actually also defined as local variables within the main loop, and not as global variables. But for nicety, really, I should have included those in the main. You'll see what we've got then is we've got we've got the simple initialized program input. We've got the simple hello world again, just that comes out just to prove it's up and running and working. But then you can see for each one of the IOs, for each one of the systems, what we're doing is we're recreating we're instantiating and configuring that instance. So, for example, for the GPIO, we're looking up we're using this function which is in the GPIO API. We're looking up the configuration for the GPIO device ID. So the device ID that's defined in the x parameters.h for channel 0 for GPIO 0, we're looking that up and storing that in the configuration, the GPIO configuration pointer, and then we're configuring the GPIO instance itself, and we're giving it the GPIO. We're configuring that GPIO instance with the configuration data and with the base address of the GPIO pointer as to where it sits in the memory map. Once we've done that, we're just using a couple of functions to set the data direction. So if you remember, we've got two channels on this GPIO. So one of these channels is actually an output channel. One of these channels is actually an input channel. So channel 1 is an output channel. So we're configuring all of the bits on channel 1 to be output. Channel 2 is an input channel. So we're configuring. Channel 1 is channel 1 drives the switches, so that's an input channel. Channel 2 is the output because that's driving the 7-segment display. So that's all set to zeros. And this structure, apart from this initialization of the direction, because we don't need to do that on other interfaces, apart from that, we follow that same structure for everything that we're doing to get the data set for all of our IPs to get set up. So you'll notice the next thing we do is we set up the video timing controller using the similar sort of structure. And this is what's actually really nice about the Xilinx environment, the Xilinx system, is that a lot of the functionality of functions, calls, and everything, they're all very similar and very same. So it's a simple concept to grasp. Once we've done that, what we're doing is we're setting up the video timing controller, and we're setting up the video timing controller to have the video mode of 640 by 480. So we're not having a hugely high resolution video mode to do this. We're having a fairly small video mode to do this. So we're going for 640 by 480. And then we're setting up the video timing controller structure. So this VTC is a structure. And what we're doing is we're setting up all of the timing information, the video timing information that's needed. So the active video width, the front porch, the back porch, the polarity of the sync signals. And we're setting all this up from this video mode here, which is defined in our VGA modes in the VGA modes.h file here. So you can see we've got all of these are defined in this the VGA modes. Once we've got that, all we need to do then is we need to tell the source the video timing controller, are you taking your information, your output timing generation that you're doing, are you taking that information from the input, so it's detecting it and just generating the timing going downstream, or are you actually taking that information from registers in there and generating your own timing because we're not using the input detection element? So what we're doing then is we just set the source select for each of these ones for the timing control, for the video timing controller, just to select that source select, such that we're saying we're running from registers, not from the input. And this is a very important thing to do. It's a very easy thing to overlook when you first try and get this up and running. So it's very simple to do. Once you've done that, we're just using a few other function calls in here to update the registers, to allow the registers to be updated, to set the generator timing that we've just wanted to set the source timing that we've done, and then we just finally call this function, this final function, and that starts the generator going. So now in our software, in our application, when it gets to this point in time, we've configured the GPIO, we've configured the video timing controller, and the video timing controller is now free running. It's now running, it's generating its timing, and it's working with the AXI stream to video output to begin to lock onto the video that's coming through. Of course, at this point in time, we've not actually given it any video to come through, so it won't lock. So this is the next element of the software that we do, is that we configure the lookup, the video mixer. So you can see here we do the configuration of the video mixer, and then we're setting up the video mixer to have the number of layers and the number of video inputs that we want. So what we're doing with the first one is we're setting up the hardware register layers to enable layer 1. Although it says 3, it's actually the binary bits that you're enabling. So we're setting up a 640 by 480 image, essentially, we're telling the video mixer that we want to mix a 640 by 480 video, and we're enabling layers 1 and layers 0 and layers 1 in this. And then once we've done this, we're telling it in the next row, so 142 to lines 142 to 146. We're telling that where the video starts in that next layer. So it starts at 00 and it ends at 640. So this is useful, not so useful for our application. But if you wanted to do picture in picture or something like that, we could do that, or tiling images together. We could do that using the video mixer. And you don't have to layer the images on top of each other. You could be stacking the images around. So we're doing that, and then we have this alpha layer. So we're applying that because we've got the alpha layer enabled. So we're applying an alpha layer onto layer 1, and we're saying, actually, you're a pretty strong layer at this. And we're doing this for layer 2 as well. We're setting up the same positions, but we're setting up the alpha layer such that it's a higher level. Although each pixel actually is going to be coming through with its own alpha pixel on it. Once we've done that, it's really quite simple. We just enable the video mixer to keep restarting every time a frame runs, so enables restart, and then we can start the video mixer running. So now there's video just about ready to be got going and streaming through our system. The final thing we do, or getting towards the final things we do to get some video going, is we set up the HUD controller to have the right number of X and Y position again. We put the ball, we start the ball directly in the middle of the directly in the middle of the frame. And we set the ball size as well. So here you can set the ball size. You can set the ball size as big or as small as you want. I set it to 5. And we set the ball color as well. Now, one thing to remember about this is we're using RGB, and it's 8 bits. It's 8 bits red, 8 bits green, 8 bits blue. But we've also got an alpha layer on this as well, because of this is the ability to mix on top of the other layer. So these top pixels here are actually the alpha they're actually the alpha values for the pixel as well. So we need to give it an alpha value, an RGB pixel. And then once we've defined the size, the configuration of the video and the positions of everything, we tell it to enable to keep running on every time it sees it, and then we start running. Once we've started running, we come into the VTC, and we finally start the generation of the test pattern video. I'm just trying to look where we are in the notes at the moment. So we finally start the generation of the test pattern video. Once we get the test pattern video up and running, and again, we're just setting this again to be the video height, the video width, and we're setting the color format to be RGB because that's what we want. And then here's where you can experiment a little bit with your design if you want. I set this to have the color bars output on the back. If you wanted to, you could have it all red or green or black. You could have the tartan color bars, and you could do some really great experimenting with that. And then we start the video. So now we've got the video timing controllers going, the GPIO all going, and we've got all the video flowing through our system. And the game, we should be able to then start running the game. What we do then is, this is very simple. We just have a very big loop. We've not gone to the depths of interrupts or anything. We've just got a very big loop here that's running round. It's reading at every 250 milliseconds. It's reading the input of the switches, so you can move the switches left and right. If you press the position switch up, then you get a longer bar. If you press the switch down, you get a shorter bar. And if you press the center switch, you reset the game, and the game will reset and start again. It will reload the application if you hit the reset. It's the master reset. Then what we're doing is we have a very simple algorithm here to work out where the ball is, the trajectory of the ball, where the ball is in terms of its position, if the position, and where the bar is in terms of the position, where the bar is in terms of where we last asked it to be, and where the ball is. And then we just draw in the depending on where that is, we draw in the ball. So we set the ball in the X and Y. We set the ball's X and Y positions. We write the score out to the LCD, to the 7-segment display, and then we move the bars in the appropriate direction as well. So we move the bar position depending on where you are. We move it by minus or plus 10 pixels each time. And again, like I say, if you press up or down, you'll change the width of the bar by plus or minus 10 pixels as well. So you can play with a large bar, or you can play with a short bar. It's up to you. Once we've got this, what we want to do then is we want to click on the build arrow here, and hopefully this is going to build. It is, and this is going to give us a new binary file. So we've now got this this updated binary. And what we want to do is we want to take that binary file and merge it with our bit stream in the application. So what we're going to do is we're going to switch back to our Vivado project, and we're going to, hopefully we've got time to do this, we're going to run Vivado through and add in, so the block RAMs that are controlling that are containing the application, we're going to put the application that we've just created into this block RAM memory here, such that when you turn on the board, the MicroBlaze starts running, it starts executing this program. So how we're going to do that is we're going to go to Tools. We're going to go to Associate ELF files, and then here, if you wanted to just do simulation, you'd use a simulation one, but because we're doing the design one, we actually want to change this one here. So we're going to click on the MB boot loop. We're going to click on Add Files on that one. And then we're going to navigate to in the workspace. We're going to navigate to that bit file that we've just created. So you can see it's 1848 in the UK time. So we're going to navigate to that file there, and we're going to click OK on that. And then we're going to click OK on that. So what that means is that when the program reruns, when Vivado runs, and it's only going to rerun, oh, I hope it's only going to rerun, because it normally does. It's only going to rerun the bit stream generation. It's not going to rerun the entire place and route. Vivado is clever enough to say, oh, you've changed the contents of that memory, therefore I can just put this application in that memory there. So we're going to click on OK. And you'll notice that it says write bitstream out of date. So what we're going to do is we're going to click on the settings tab here, because we need to make a slight change. At the moment, we're getting a bin file, a bit file out, which is the bit file that we can program in. We also need a file that we can program into the Qspi flash on the board. So what we're going to do is we're going to click on the bitstream options here, and we're going to select the bin file as a type that we want, and we're going to click on OK. And then we're going to ask it to rerun. We're going to ask it to rerun the design, regenerate the bit stream. And this should take a minute or two to do. If you got this, now is a great time to ask any questions. If anybody's got any questions. So Ken just asked a question about what do you do if you start with C, C++ code, and what program or function do you use to create the hardware and software for the board? So to create the hardware for the board, we use Vivado. And I don't know if you were present in the previous lab or not, but if you look on the link we put up the top to YouTube, you can see the start of that. You can see a link to the video that showed you how you go through Vivado to create that hardware element there. Once this is completed, you'll see this button, this dialog pop up. What we want to do is we want to open the hardware manager, and we're going to click OK on that. Now, if you've turned your board on or off, so the BSP for the hardware can be exported. And you can do that. I'll run through this and show you how to do this, because we're getting a little late on time. And then if you hang around towards the end of the lab, I'll show you how you can export that BSP for export once we've just done this. Now I've still got my board here. I've just turned it back off and on again. You know, you can see the red light. It's still set for JTAG programming. So what we're going to do is we're going to open target in the hardware manager. We've opened the hardware manager. We're going to click on auto connect, and you'll see it come up with the device that's on the Artix device that's on the Basys3. What we're going to do is we're going to click on that. We're going to right click on that device, and we're going to click on add configuration memory, and here is where we're going to click on the relevant Qspi. We're going to need to add in the relevant Qspi device. So the name is Macronix. The density is 32. So you should see that we have two options here. The MX25L. So I'm going to click on this one at the top and click OK. And then it's going to ask me if I want to associate a programming file with this one. And yes, I do. I'm going to click OK on that. And then I'm going to point it to the bin file that I've just created. Now that's actually going to be under, it's going to be under the project directory, the Vivado project directory you've created. It's going to be under the runs directory, and it's going to be under the implementation directory, and it's going to be the design1 wrapper.bin that you can see. And you can see the time there was 1851, so a couple of minutes ago. So if we click OK on that, and then we'll leave the options as they are. And what we don't want to do, obviously, we don't want to change or interrupt any power or anything to it while we're doing it. But we'll click OK, and hopefully we'll see this. We'll see this run through. We'll see it erase. And unfortunately, at the end of this, I can't show you this working, but I can show you the video of what it looks like when it's working. Purely because the main monitor that I developed this on is the one that all this application is running on. So you can't see. But it will give us this part. It will give us the Pong game. And we'll be able to see that. So it's running through and it's programming. It's not a huge file, so it doesn't take too long. To download. Oh, I hope it doesn't take too long to download anyway. But it's running through. It's nearly done now. You'll notice that it downloads a program. Hopefully you'll see this flash programming completed successfully. And then we can press OK on that. Now, what we can do then is, I'm just going to open a terminal and clear my screen. What we can do then is if you look at my board in the camera, we're going to turn the board off, which killed the terminal. You're going to get a warning if you turn it off from Vivado Hardware Manager. I'm going to take that jumper off of jumper 1, and I'm going to connect it back across the top 2, such that it works for the to boot from the Qspi, and then I'm going to turn it on, and we're going to wait a minute or two. While it comes through. In fact, I'm going to close my hardware manager just to make sure that that doesn't cause a problem. Let's set that up. I did set that up right, didn't I? I'm going to turn that off and on again, actually. Turn that off, on again. Give it a second, and what you'll see is you'll see my games come up. Now, you have to make sure the hardware manager is disconnected, otherwise it'll stop the MicroBlaze from booting up. You'll see that I've got a score that's appeared on there because it started to play already, and I've just died, so the score's been reset. And you'll see the application run around, and you can move the buttons as you press the 2 buttons. You'll be able to move those about on the application, and you can see there were some commands I put in the software code to tell me the status of it. So you can see the information here on the test pattern generator and the output is that. So what I'll do very quickly, let's try this. I really don't know if this is going to work or if this is going to kind of terminate the session early because it's my main computer screen. But let's take a look at the video that it should do, and we'll pull that up. So if this has run through successfully, what we should be seeing is we should be seeing a game. We should be seeing exactly this game as you can see on the screen, where it's running through. You can hear me pressing about. You can see the ball batting about and bouncing off the edges of the screen, and the counter going up and down. If you've had any issues building this, then the solution is also if I go to my GitHub again. And you can, just to prove that that's working, you can see me doing it there. We'll close that one. But if you go to my GitHub, if you've cloned this repository, if you've not cloned this repository, under here you'll be able to see the solution, the design wrapper.bin. So the final file that you program in to make this work is all included in the design wrapper, and that kind of takes you to the end really of creating the game. And I'm going to pass the ball to you a little bit now and ask you what you'd like to do with it, and see what you'd like to do with it. So somebody just asked what the bin file contains exactly. The bin file just contains the bit file, but correctly formatted, but in such a format that it can be written into a memory. Excuse me. So it will tell you that, and it will put that in there. So somebody's just asking, how do you know about the manufacture of the Qspi memory? And that's a great question. So let me show you that. Let me show you that at the moment, because it is a it is a question that you'll get, and as with all of these things, actually, I think there are 2 versions of the board. So let's have a look at support material there, resource center. So you can see the example here. So this is the Basys board here. Let's go to the reference manual. And in the reference manual, it should tell you. It'll say. So this is the actual one on the. Just put it back to the screen. So this is the actual Qspi chip on the bottom, and I think on this version there are 2 versions. So this section here, let me put this in the chat for you. But this section here will tell you which of the Micronix which of the flash devices you've got fitted, whether you've got the Micronix flash or the Spansion flash devices fitted to your board. So is there any questions as we work through this? I know it's been a bit fast paced. Obviously, it's not quite as fast paced as the first session. That was particularly drinking from a fire hose. But this one's been good fun, and it wraps it up nicely. I mean, the Basys board. If you're just starting out with FPGAs, you know the Basys board's a really nice. It's a really nice board to work with and to do, particularly because you get these switches and the LEDs. And when I was first approached about doing this webinar, I was like, well, we'll do a calculator or something. But actually, you know, the little Pong game really shows off its capabilities. There's also the PMODs. The PMODs are a great interface on there, so you can interface PMODs to it, and you could make adaptions to this game to use perhaps the PMOD joystick to allow you to position to move the baton ball about if you so wanted to. And you can also plug in a USB keyboard and mouse if you want to, so it'll do a PS2 P2S interface there as well for that. So that really wraps it up and brings us through to the end of it. There was one question earlier on about exporting the hardware from this. What you can do is, let me just go and tidy this up a little bit. But underneath this hardware platform here, you can actually export as archive. You can export the platform project as an archive, and that'll give you a compressed file that you can use and share with people, and pull that and share that across other projects. Once you've got that, it's going to give you this zip file. I'll click on cancel there. I'm not actually going to do it, but once you do that, you can then import it into your file system by going into the import sources option and browsing to it and pulling it into the device. What we'll do, so this is, like I say, this is, as Megan was just saying in the chat, this has all been recorded, and we'll put it out on we'll share it on my website and on the YouTube channel that you've got. So if you've got the first element, you can see it. Ken, you asked a question upstream about building the when you start with C++ code and how do you create the hardware or software for the board. Did I correctly answer that with talking about Vivado, or was your question slightly deeper than that? If I didn't quite answer your question, please pop it in the chat, and I'll try and take it a little bit more and answer a little bit more from there. I can see someone's typing, so I'll just hold off to see what question they're asking for. Yeah, the video will be up. I will just keep an eye on my channel, or if you want to subscribe to my channel, that'd be wonderful. But the video will be up this evening or tomorrow. And you've all got my email address. You know, quite a lot of people reached out after the first session and asked me questions over email, and we've done that. Unfortunately, you can't program the Carlos. Unfortunately, you can't program the MicroBlaze or the ARMS or anything using the Arduino IDE. You really need to use this Vitus IDE. What you can do though is, I mean, you can customize this IDE and you can actually pull it into things like VS Code if you're working with VS Code. You know, it's all kind of open source and flexible, so you can pull it into that. Richard, I'm glad you had a good time. These are great boards. These are really good. These are really good little boards. You know, that little microprocessor in there, and we've taught you a lot. I was hoping we might have a little bit of time to talk about the high-level synthesis side of things, but we've run through that. So, just to come back to your question, Ken. So Vivado is where we captured the design. You know, we did the in lab 1. It's where we captured the design. It's where we created the block diagram, where we put the MicroBlaze in there and so on, and that's all working in VHDL, in RTL, and in the outputs from the high-level synthesis tool. Vitis is where we're taking what we export from Vivado is a hardware definition and a bit file for the FPGA, and we bring that into Vitis, and it's in Vitis is where we write the software, the C, the C++. The only difference to that is if we were to use high-level synthesis, then we would use Vitis high-level synthesis to take a C or C++ algorithm and compile that into a RTL description that can be pulled into Vivado. And that you can see in this example, you can see that there and the HUD generation. And that, if you go take a look around around the GitHub, you'll find all the code for that HUD and for everything else is available on my GitHub as well. So you can take it in, and you can run through that and explore that to your heart's content. Okay, if there's no more questions, then I will thank you all. I will thank you all for attending. I'll stop sharing the screen for a second, and you can get me in full view. I'll thank you all for attending. It's been really good for me. I've really enjoyed creating this and putting it together. If you've got any questions, like I say, just reach out and we'll take it from there, and we'll get something fun and up and going. And Michael, I'm glad you've enjoyed it. I enjoyed it tremendously creating this. It's quite nice to sit and create a little game, a little fun game. And I'd really be interested, you know, if you do get it up and running and play with it, I'd really be interested to see what you do with it, if you can take it and adapt it, because I hoped I created a little game that you could sort of run with a little bit and add your own elements into it. So right, with that, I'm going to end this session. Keep an eye on my channel and we'll be uploading it. But thank you very much for coming, and stay safe all, and I'll speak to you all soon. Thank you very much. Bye-bye.